Imagine a world where your smartphone never runs out of battery. Picture computers that process information at the speed of thought. Envision a future where data storage is virtually limitless. This isn't science fiction, my friends. This is the promise of Spintronics. Traditional electronics rely on the charge of electrons to function, but Spintronics? It harnesses the spin of electrons. Spin is an intrinsic property of electrons, just like charge. But unlike charge, spin can be manipulated without moving the electron. This means we can process information with less energy and generate less heat. Quantum computing, ultra-dense data storage, and even neuromorphic computing that mimics the human brain. These are all within reach thanks to Spintronics. Let's dive a little deeper into the quantum realm, shall we? To understand Spintronics, we first need to grasp the concept of electron spin. Electrons aren't actually spinning like tops. It's more of a quantum property, an intrinsic angular momentum. Think of it as a magnetic moment that can point either up or down. In traditional electronics, we only care about the charge of electrons. But with Spintronics, we're suddenly playing with the full spectrum of colors. We can manipulate the spin state of electrons, creating a whole new way to encode and process information. One of the key principles in Spintronics is spin polarization. This is the process of aligning the spins of a group of electrons. Once we have a spin-polarized current, we can use it to carry and process information in ways that were previously impossible. Now that we've got the basics down, let's look at how Spintronics is already changing the tech landscape. One of the most exciting applications is in data storage. Hard disk drives have been using a simple form of Spintronics for years. The read heads in these drives use a phenomenon called giant magnetoresistance, or GMR. Magnetic Random Access Memory, or MRAM, is where Spintronics really shines. MRAM uses magnetic elements instead of electric charge to store data. It's non-volatile, meaning it doesn't need power to maintain its memory. It's also faster and more energy efficient than traditional RAM. Spintronics is also making waves in the world of sensors. Spin-based sensors can detect extremely weak magnetic fields, but perhaps the most exciting current application is in the field of neuromorphic computing. Section 4. Recent breakthroughs, pushing the boundaries. The world of Spintronics is evolving at a dizzying pace. Every day scientists are making new discoveries and pushing the boundaries of what's possible. One recent breakthrough comes from the University of Cambridge. They've developed a technique to control the movement of domain walls in nanowires using electric fields. Another exciting development comes from the world of two-dimensional materials. Researchers have found ways to induce and control spin currents in graphene. By combining graphene with other materials, scientists have created spintronic devices that are just a few atoms thick. In the realm of quantum computing, Spintronics is making significant strides. Scientists at the University of Chicago have demonstrated a way to read the spin state of a single electron. This is a crucial step towards creating quantum bits, or qubits. Qubits are the building blocks of quantum computers. With spintronic qubits, we're inching closer to practical quantum computers. But perhaps the most mind-bending recent breakthrough is in the field of skyramions. Section 5. Future Impact, a quantum leap in technology. As we peer into the future, the potential impact of Spintronics is nothing short of revolutionary. One of the most promising areas is in energy efficiency. As our world becomes increasingly digital, the energy demand of our devices is skyrocketing. Spintronic devices could dramatically reduce this energy consumption. But energy efficiency is just the tip of the iceberg. Spintronics could usher in a new era of computing power. Quantum computers powered by spintronic qubits could solve problems that are currently intractable. In the realm of artificial intelligence, Spintronics could be a game changer. And let's not forget about space exploration. Section 6. Overcoming challenges, the road ahead. Of course, the path to this spintronic future isn't without its obstacles. One of the biggest challenges is temperature. Many spintronic effects are only observable at very low temperatures. Room temperature spintronics is the holy grail, and scientists are working tirelessly to achieve it. Another hurdle is scalability. While we can create amazing spintronic devices in the lab, scaling them up for mass production is another story. Integration with existing technology is also a significant challenge. Our current infrastructure is built around charge-based electronics. Transitioning to spin-based systems isn't as simple as swapping out a few components. Lastly, there's the challenge of education and workforce development. Section 7. Conclusion: spinning towards a brighter future. As we stand on the brink of this spintronic revolution, I can't help but feel a sense of awe and excitement. We're not just talking about incremental improvements here. Spintronics has the potential to fundamentally reshape our technological landscape. The journey ahead won't be easy. There are significant challenges to overcome, from the fundamental physics to the practical engineering. But that's what makes it so exciting. Every obstacle is an opportunity for discovery. Every setback, a chance to learn something new. As we move forward, it's crucial that we approach this technology with wisdom and foresight. The power of Spintronics could be used to create a more sustainable, efficient, and connected world. So, let's give it a spin, shall we? The future is waiting, and it's looking brighter than ever.